Okay, it is about 2 o'clock for those watching. So we can begin. We'll address the time later. But for now, our lesson will continue with how we are viewing functions so far. And later on in the lesson, we will learn about two functions, continuing on with 1 over x and x cubed. And by extension, possibly x to the 4th. So last week we reviewed some important concepts such as domain and range. Whereas domain represents all x values where the function is true, essentially. Or rather, when the function continues. And range is the y version of domain, so all y values the function reaches. So if we are to view this with a normal function, such as, let's say, y equals x plus 1, if we draw out our function, it will look like this. And if we were to analyze its domain, where the domain is all the x value that the function reaches to, we see that the function, the line, it goes in the negative x direction forever and the positive x direction forever. So its domain is from negative infinity to positive infinity. And this is where sets come into play that we talked about earlier in one sense. And for the range, we have to analyze all the positive direction and the negative direction that the function extends to. And since it goes negative forever and positive forever, so we know that it touches all y values, the range is from negative infinity to positive infinity. Any questions so far?
No, sir.
Okay, good. So let's make a little bit of room here. And let's analyze the function I equals x squared. in terms of its domain and range. Mr. Raj, do you happen to know what y equals x squared will look like?
No, sir.
I would suggest, if not, maybe review the lessons on YouTube so you can get a good understanding of it. But in general, what you need to know is that whereas y equals x squared, it will look like this. Where the y where the y position of the function is equal to the x position squared, and it'll come out to a shape like this. Now, Mr. Raj, you remember domain and range properly, yes? I'm sorry, Mr. Raj, I couldn't hear you.
Yes, sir.
Okay, so Mr. Raj, could you start us off with what the range should look like? Okay, so we said that the range describes all the y values that the function can touch. So we can see here that the y value would be at 0, and then we can see that it will rise and it'll go up forever, correct?
Yes, sir.
Okay, so if it's at 0 and it goes up forever, does that mean that it will probably extend forever in the y direction, so it'll touch all positive y values?
Yes, sir.
Okay, good. So we can say that the upper limit of the range would be towards infinity. Now, what would you say that the lowest y value would be of this function?
0.
0, very good. So because the function touches 0, we will put a bracket so that it says that the function does touch 0, but it doesn't touch infinity, that it is the range of bracket 0 to infinity. So this says that all the y values of this function is not negative. So we know that it touches 0 and it'll go for all positive y values. That is what we understand from this range. Any questions so far?
No.
Very good. So now we need to do domain. Would you have any idea on how to do this, Mr. Raj?
Sir, I don't really have no idea. The way we did domain and range, it was different.
Okay.
It wasn't this complicated.
I understand. So, what way did what ways did you guys do domain and range? Would you happen to be able to tell me? I'm sorry, I couldn't quite hear you. Okay. Everybody has different ways of learning these things, which is fine, of course. But I'm not quite sure how it might have been taught over there. But I'll do my best to try and make it less complicated. So the range, as we said it, was that we know that the function can be any of these y values. So we can say that for any y value in between 0 and up to infinity, there will be an x value which you can put into the function and you'll get the y value. So the range says that, let's say, the range says that at y equals 16, there will be an x value to go with it. So that means that we can put this 16 into our function and get 16 equals x squared. And if we solve it, we would get positive and -4 are the x values where y will equal 16. So the range says that for any of the y values from 0 to infinity, so all the positive numbers and 0, if you put these y values in the function, there will be an x value where we can answer the function with. So these are all the things you can put in the function. But as we can see, because we do not include negative numbers in our range, that says that if we tried to use negative numbers, so let's say y equals -1, and we try to put in our function, we would have to find the square root of -1. This does not work because we do not know how to do this. So this says that because -1 is not in our range, that the negative numbers for the y value cannot be put into the function to get an x value. There are no x values where we can find that y will be equal to, in this case, -1. And for the domain, it is essentially the other way around. The domain says that the domain is where we can put in an x value and it will come out to be a y value. So, and this will be represented for all of the places on the x-axis where the function will go to. So we want to think about, are there any x values that we can put into this function where it cannot get a y value? Now, Mr. Raj, do you think that there are any x values that you cannot put into this equation to get a y value?
A negative number.
Okay, we can try that. So let's try and put in a negative number. So let's say x is equal to -1. So if we put that in, so y equals -1 squared, -1 squared will come out to y equals 1. So that says that at x equals -1, we can get an answer for y. And it will work for all of the negative numbers, 0, and all the positive numbers. So it will go from -infinity to +infinity. The reason why is because there's no reason why we can't put any x value in to get a y value. However, range is different. because the domain says that this is all the things you can put into the function. The range is saying all the things that you can get out of the function. So I can put in anything I want into this function because there's nothing saying I can't. However, there are things saying that you can't get certain things out of the function. And you can see it because the y never goes below 0. And because of that, we can see in our function that we cannot get y equals -1 out of this function because it never goes down there. And because since it is x squared, we would have to square root a negative number, which cannot be done to find x. So this is saying that if we were to try and look for an x value, so that if we put it into this equation, it would become y equals -1, we can't find any x value where we get y to become -1. Does that make sense, Mr. Raj?
Yes, sir.
Okay. So domain is all the things you can put into the equation. Range is all the things you can get out of the equation. Now, Mr. Raj, if you remember from the real number sets that we did before, do you remember what describes all the numbers from 0 and all the positive numbers? What we call them? If not, that's fine. It was a while ago. If you remember.
Excuse me, sir. Could you repeat the question? It was breaking up a lot just now.
That's fine. Do you remember what describes all positive numbers and including 0 from the real number
All
system?
positive numbers and including
Yes.
0. So whole number.
Very
whole
good.
Numbers.
So the range describes all whole numbers. Now that's if we ignore fractions, but this is generally what I want. This is generally what I care about. So it would be all whole numbers, being that it does not include negative numbers. And if we were to include fractions, it would be all non-negative integers, or non-negative real numbers. Okay, sound good?
Yes, sir.
Good. And for the domain, it is all real numbers. So sometimes you can answer with sets, such as this, which describe the range and the domain, or you can answer by saying, in this case, non-negative real numbers, or in this case, all real numbers. It's kind of a matter of preference. I personally prefer to use the sets because the categories of the real number system are implied, but it all depends. It's just so long as you recognize when they say all real numbers or non-negative real numbers whenever they give you a problem. So do you have any questions so far about this?
No, sir.
Very good. So from last week, we ended off by introducing ourselves to another new function, which was, oops, which was the function, which is y equals 1 over x. So function, if you remember, is just the same as saying y equals. So y equals 1 over x. So people do not inherently know what this function will look like. But there are ways of figuring it out. So let's think about it for a little bit. So we don't know what the shape is. But we know that there are some critical pieces of information about functions. We can know what the shape is, the x-intercept, the y-intercept, the gradient, and we recently just learned domain, range, and something called continuity. Now, if we look at the word continuity, it looks like continue. And the reason why is because continuity means all of the places where the function continues. So if there is, for example, an x part of the function where we can't put something in the x part, that means the function is not continuous at that point. Or in other words, continuity means all of the places in the domain. So these are, for now, essentially the same thing as far as you're concerned. So we don't know what the shape is. We do know that the standard form of a function is y equals b plus mx. So this is all the information that we learned so far. And there's one other thing. We have learned before that to understand what a function looks like, what we can do is that we can take some sample points. So if we have a little chart and we have x's and y's, we can take samples of x values and find their y values to understand what the function might look like. Does that make sense?
Yes, sir.
Okay, so we want to find data points in a sense. Mr. Raj, would you like to try out 5 x values so we can understand what the function might look like?
Five different numbers.
Yeah, 5 different numbers to put in the x-axis. What 5 numbers do you think would be good to find out as much information as possible?
1, 0.
Okay, those are good. So 1 and 0. So we got a positive value and we got 0. And 0 will be good because 0 will hopefully tell us what the y-intercept would be. So what are some other good numbers?
-2.
-2 is a good one. So we got so now we got a negative to work with. Let's take 2 more just to be safe. Tell you what.
5 and 8.
5 and 8, all right. So we have from our sample points, 1 negative, 0, and 3 positives. Would you like to just work with this, or would you like to have 2 negatives to balance it out?
Yes, 2 negatives.
Okay. It's not a rule. It's not a rule. It's just a matter of preference. So as we have it here, we have our 0, we have 2 positives, we have 2 negatives, and this will tell us a lot about our function. Let's switch around this -5 and -2. So we have left to right some values of the function. So we'll find it for -5 and -2. All right. So the very simplest one to start off with would be 1, probably. So what we can do is we'll extend our graph a little, and 1, 2, 3, 4, 5, 6, 7, 8. Okay. 1, 2, 3, 4, 5, and we'll give ourselves some y values. 1, 2, 3, 4. 2, 3, 4. So which one of these would you like to start off with first?
1.
1. Okay, good. So let's start off with 1. So here's our function y equals 1 over, and our x would be 1. So what would this come out to?
Pardon me, sir?
What would this come out to? We have our function here, and we are testing it for x equals 1. So this is what it will look like. Y equals 1 over, and in our x, we put 1. So 1 over 1. What will this equal?
Equal to 1.
Very good. So it will be 1. So we can put this in our chart here. So we know that here is our 1. So at 1, it will be 1. So this is where the point will be. And let's label it 1, 1. Very good. So we can get rid of this. Make up a little space. What would you like to try next?
Zero.
Okay, let's try 0. So y equals 1 over, and substituting, we put 0. So what would this be? Do you have any ideas, Mr. Raj?
Not sure, sir.
Okay, that's perfectly fine. So 1 over 0 looks tricky because we don't know off the top of our head what it would look like. If we were to try to do the division, so 0, 1, oops. If we try to do the division 0, 1, we wouldn't know what to do in this situation. So in instances like this, there is a certain method that we can apply. We know that 0 is less than all the positive numbers. So on our number line, we have 0 and we have 1. If we get closer from 1 to 0, we should hypothetically get closer to what 1 over 0 would be in this case. So what we can do is that we can look at values of 1 over x, and we can use 1, we can use fractions and smaller fractions until we get to 0. So then we might understand what it might look like. Does that make sense?
Yes, sir.
Okay. So we did 1 over 1 already, and we know that that equaled 1. So if we try to get a little closer, let's try y equals 1 over 1/2. Because since 1/2 is closer to 0, then that means this will be closer to this than 1 over 1. So what would this be? 1 over 1/2. Do you happen to know how to do this one, Mr. Rash? I'm sorry, I couldn't hear you. Okay. So let's think about it this way. If we have 1/2, this will come out, this is 1/2. We know how it works. Let's look at the denominator. We know that the bigger the denominator gets, the smaller the number will be. But the smaller the denominator gets, the bigger the numbers will be. So if we were to multiply the denominator by 2, so 2 times 2, it will become 1 over 4 because we multiplied it essentially by 1/2. So if we multiply the denominator on the bottom by 2 in this case, it becomes half of what it originally was, 1/2. Let's think about it this way, however. What would happen if we divided the denominator? Well, in this case, it was 2 originally, and if we divided that by 2, we know 2 over 2 is 1, because anything divided by itself is 1. So this will come out to be 1 over 1, which is 1. We did this before. So what happened is that when we divided the denominator, originally it was 1/2, but now it's 1. So what we can understand is that if we divide the denominator, in this case, then we multiply the whole number. So because we divided it in half, we actually doubled the whole number in this case. So now we have 1 over 1. And in this is 1/2. So what we're doing is that we're trying to divide it by 2 again. So, Mr. Raj, if we double the number every time that we divide the denominator by 2, what do you think will happen when we divide the denominator by 2 again?
Double the number again.
Exactly. So 1 over 1 was 1. So if we divide the denominator by 2 again, you said that we would double the number again. So what is 1 doubled?
2.
Very good. So that's what's happening here. So when we got closer to 0, by instead of having 1 over 1 and we change it to 1 over 2 in the denominator, we got 2. So as we got closer to 0, our number increased. So let's do it again. Instead of 1/2, let's make it 1 over 4 in the denominator. Mr. Raj, do you think you know what this would be?
3.
Hmm?
3.
Well, let's think about it. Originally, we had 1 over 1/2. And this was double of 1 over 1. Now we got 1 over 4. When we did 1 over 4, did we half the denominator, 1/2 to 1/4?
Yeah, yes, sir.
Okay, so it would probably
Yeah.
double again.
Yeah,
Okay.
it'll be 4.
Very good. So there's a specific rule about this called keep change flip. So what it is that on the top, the numerator, what you do is that you keep the numerator. Instead of dividing, you change it so that it is multiplying by, and the denominator, you flip it. So this would be 4 over 1. This is the same as this. Does that make sense, Mr. Raj?
Yes, sir.
Okay. So keep this in mind as we go forward. So as we saw, as we got closer to 0 again, we raised our number. So instead of 1 over 4, and instead of having the denominator again, let's go straight to 1 over 10. So Mr. Raj, use keep change flip and figure out what will this be.
Sir, I can't really see the numbers on that side of the board. It's a little bit blurry.
It's a little bit what?
On the side of the board that you're writing, it's a little bit blurry.
Oh, I see. Okay. Does that look better?
Yes, sir.
Okay. So can you use keep change flip to find this?
Yes, sir. Just give me a minute.
Did you get anything?
Yes, sir. It will be. Is 20 correct?
It will be 10. Okay, so yes, we kept the 1. Instead of dividing, we changed it to multiplying, and the bottom, we flipped it to 10 over 1. So when the numerator is, when the denominator is a fraction like this, we keep the numerator, we multiply it by the denominator flipped over, and that's how we did it. So good job. 10. So what we saw is that as we got closer to 0, again, what happened is that each time we got closer to 0, we keep increasing. So this is what the function will look like. The problem is that as we get closer to 0, all it does is that it just keeps increasing. It doesn't get closer to any one thing. And this doesn't help us because it doesn't look like it's getting closer to any one number. All it does is that it just keeps on increasing and increases more and more rapidly as it gets to 0. And if we do this with negative numbers, all we do is that we just put a minus sign on it. So that means that it'll, from the negative side, it'll just go down forever too. So now we have a problem because from the positive side, as we get closer to 0, it just increases forever. And if we were to do the same concept with negative numbers, all we would do is just put a minus sign and it'll come out to the minus number. So it keeps going down forever too. So this means that there is no value for 0. DNE means does not equate. Or I'll just put NA for not available. So we can see that there is no value for 0 available because there's a paradox here. Now, as we are right here, we want to stop for a second because we found a spot where on the function does not exist. That's what it's for. So because it does not exist at 0, we need to put that in our domain right now. So domain is unequal to 0. That's what we got so far. Does that make sense?
Yes, sir.
Okay. So we have to move on from 0 here because we're not getting any closer to anything from here. But there is something noteworthy here. Could we tell anything about the range so far? Mr. Raj, are you there?
Yes, sir.
So far, does this tell us anything about the range?
Sir, one is within the range.
Okay, true. We see that 1 is included in the range. Not only that, but from our experiments with trying to find out what 1 over 0 is, we saw that the function kept on going up forever. So what we know so far is that for the range, we know that it does go from 1 to infinity so far, just from what we've seen so far. So we somewhat understand what the function looked like. And because in our experiments, we could put a negative sign on the function and it would come out to the same negative numbers, we could figure out that the function would exist at -1, -1 too, and it will copy this down here. So we could also see that the range will go from -1 to -infinity down here. So that's just what we understand about the range so far. And with the domain, we saw that the domain does not include 0 so far. So Mr. Raj, what numbers would you like to go for next?
Yes, sir, to -5.
-5? Okay. 1, 2, 3, 4, 5. Okay, so the function will be y equals 1 over and substitute in -5. So Mr. Raj, what will this come out to be? Mr. Raj?
Sorry, I'm not so sure.
Okay. I think you said yes, it will come out to be just -1/5. So yeah, as we go forward to -5 over here, we trace a line and we say that at this point, it is -5 and -1/5. So that is our coordinate for right there. So that's what we can put here. Okay. So let's do 8 now. So if we do 8, we can solve for y equals 1/8. And that'll simply be our answer, 1/8. So we can just draw over to our 8 value. And we can say that here is, I'll erase this for room. Here is simply 8, 1/8. So that's what it looks like when we approach over here. And what we can see here is that this goes on for forever. As we put in bigger numbers in the x value, the y values just get smaller. And it happens the same in the negative direction. But what we've also seen is that when we put small numbers like fractions, the function just gets big as it approaches 0. So this is a function that we're left off with. So Mr. Raj, do we think that we can just put any x value other than 0 into this function forever? Will it just keep on giving us smaller and smaller values?
Yes, sir.
Okay, so we said that aside from 0, we can just put in any positive number we want, because all it'll do is that we'll just keep putting in bigger and bigger positive numbers, and it'll just come to smaller and smaller answers. And if we can do that, we can do the same thing with negative numbers too. So this means that the domain of the function will be essentially all the negative numbers you want to put in and all the positive numbers you want to put in, as long as it's not 0. So in the end, our domain is, in fact, x is n equal to 0. Because aside from 0, there is no other number that we can tell that this function says we cannot put into it. 0 is the only number that we cannot put into it. Now, as we've seen so far, we saw that we couldn't put anything for x is equal to 0. So what we've seen so far is that, no, not that one. The y-intercept does not exist. So, Mr. Raj, so far we understand what the domain will be, and we understand the y-intercept does not exist. Can we figure out anything about the range now?
Start ranges from 1 to infinity.
Okay, that's true. We know that the range goes from 1 to infinity because of what we tested, and we saw that it also goes from -1 to negative infinity just from putting a negative on it. But also what we saw when we did 8 and -5 is that we got small fractions too. So that means that we have lots of fractions in our range as well, correct?
Yes, sir.
Mhm. So we know that we have essentially all the positive fractions and negative fractions we can get from simply plugging them in to the x value, and we'll keep on getting y values out of them. So we know that not only do we have all positive and negative whole numbers, we have all positive and negative fractions as well, because we can just put in the fraction. So because we can find all the positive and negative fractions, the only thing left to find is 0. So can we get 0 for our y? That's what we have to ask ourselves. So Mr. Raj, how do you think we can try to find out what x would have to be to equal y?
I'm not sure, sir.
That's fine. Could we use our equation by plugging in 0 for y?
Yeah.
Okay, because the that's the good part about having the equation. If we want to know what x might be to equal y, well, we can just substitute in 0 for the y and solve for the x. So let's do that. So we want to put in 0 where the y was equals 1 over x. So now we have to solve for x. Now what we can do is that we can, to try and get x by itself, we can multiply x over to this side. So it will come out to be, let's make some room here. X times 0 equals 1. So that's what we have now. This equation says that when y is equal to 0, x must be a number where that number times 0 equals 1. Now, what do we know about a number times 0?
It's equal to 0.
Exactly. A number times 0 will always equal 0. But in this equation, it says we need a number times 0 to equal 1. The problem is that such a number doesn't exist because of the rule, a number times 0 is 0. So because of this, we can say that there is no y, there's no that there is no x where we can get y as 0. So that means 0 cannot be in our range because there's no y, there's no x to go with that y. So that means y cannot equal 0 for our range. But we said before that we can find all the negative fractions and positive fractions and positive whole numbers and negative whole numbers in our range and our domain, but we cannot get 0 for either of them. So now we have, oh, and because we cannot find y equals 0, then that means there is no x-intercept. So the x-intercept does not exist. So all of this information that we found tells us that our function essentially comes down to this. For y equals 1 over x, here's what our function will look like. We said that y could never be 0 and x can never be 0. So the function will never touch either of these lines. But what we did see is that the y, the function will go up forever in the y direction, and it'll go forever in the x direction, but never touch it. And similarly, it will go forever in the negative x direction and the negative y direction, but never touch it. And because it never touches the zeros, it can never be in the this quadrant or this quadrant because it can never cross the x or y axis to reach them. And the function cannot exist here because then it would not be a function. It cannot coexist with these parts. So that means this is what our function looks like, where it can go up and down in the y direction forever, but just never touch 0, and the same with the x. Does this make sense? Do you have any
Yes,
questions?
sir. No, sir.
Okay. So this is a little food for thought. And this is how we used all of the information here to find out how this will work. The only information here that wasn't relevant was the gradient. Now, the gradient will apply in the future to other functions, but this function in particular will not be affected by the gradient because of the nature of it. But in the future, we will run into having to use gradient further. But that is how we found the shape using our understanding of the x-intercept, the y-intercept, the domain, and the range. And we can say that the function is continuous in the exact same way that the domain is, so that the function continues for all of x values that were not 0. So that is how we use the domain and the range. So it is 2:01, so we can take a break until 2:06. Does that sound good?
Yes, sir.
Okay. Okay. Right there, Mr. Raj? Mr. Raj?
Yes, sir, I'm here.
Oh, my internet. Okay. So we went over a lot today, so I won't go over too much more. So there's one more thing to learn about in terms of information, and that is asymptotes. So normally I like to break down the words to try and further understand the meaning, but I'm not quite sure about this one. It's spelled A-S-Y-M-P, asymptotes. So what I can see is that the beginning word is asym, and this is similar to asymmetrical. So I think from here, or a symptom, so asymmetric or asymptom, this can refer to the fact that in the domain or the range, an asymptote is a line that shows where the function does not exist. Or where the function can't exist. That makes more sense. So an asymptote, if you look at asympta as an asymptomatic, an asymptote could mean that this line shows where the function cannot exist. So it is asymptomatic of existing where these lines are. So for example, we can review the function that we just went over. Both of the functions that we went over today, y equals x and y equals x squared and y equals 1 over x, both have asymptotes. Not so much x squared, however. That's a little bit different. But y equals 1 over x has 2 asymptotes. So we said with y equals 1 over x that y cannot be 0 and x cannot be 0. So let's say that y equals 0. Could we actually plot this on a graph, y equals 0? Mr. Raj?
Sir, but yes, sir. It will just be at the center where the 0 is.
Very good. So y equals 0 refers to all of the points on the graph where y equals 0, which is the center and the x-axis, because the x-axis describes all the points where y is 0. So at the origin is 0, 0. At -1, 0, y is 0. At 1, 0, y is 0, and so forth. So y equals 0 will be, sorry, y equals 0 is the x-axis. So if we were to draw it, it would look like, or let me use a different marker. Y equals 0 will be this black line. So all of this. So if we went further and we said if x was 0, this would be all of the y-axis. Y equals 0 and x equals 0 are actual lines that we can plot on the graph. And they will look like this. When you say y cannot be 0 and x cannot be 0, that means that the function can never touch either of these lines. In this case, the axis. Does that make sense?
Yes, sir.
Okay. So keeping this in mind, when we draw our function y equals 1 over x, we want to draw our function avoiding these black lines. However, one thing about asymptotes is that when a function cannot be at this point, the function tends to approach the asymptotes because of the nature of asymptotes. They will keep going forever and ever until they get really close to the asymptotes, but they will never touch the asymptotes. So in the future, if you can identify points, lines where y cannot be a number or x cannot be a number, then that will tell you more about your graph, because you will recognize that y cannot, that the function will approach these asymptotes in these ways. So that's a different way of looking at the graph. In the case of y equals x squared, where we had our function y and x, we had our function look like this. What we notice is that y cannot be negative, or y cannot be less than 0. So that could be a way of writing it. So the way this would translate is that y cannot be any of the points where y is less than 0. The thing is that this covers all of this, because we said that it cannot be less than 0. So less than 0 covers a lot more than just 0. So that's why it will be all of this instead of just a line. But what you can say is that y cannot pass this itty bitty boundary right next to 0. And that's what you could technically maybe say is something of an asymptote, but it will not work that way usually. So the idea is that if this line were to represent the very first negative number next to 0, the function could not pass it. So that would be similar to an asymptote. But all in all, an asymptote is a line that shows a barrier. So let's apply this to a modified function. Let's say y equals, let's be uncreative and say 1 over x minus 1. So ignoring how we would draw the function, let's try and just figure out what the asymptote would be. So how could we determine where the asymptote is? We would have to see this function and we would have to understand what rules in math could be broken here. So one such example is before when we tried 1 over 0. Because earlier when x was 0, when it was just 1 over x, and we wanted to find out what x was when it was 0, we had this, and we said that we can't do anything with this. Does that make sense?
Yes, sir.
Okay, so one thing we can do is that we could try to figure out when does this happen in the function. So because the function, the fraction, is in terms of 1 over x minus 1, could you tell me, Mr. Raj, what would x have to be so that this would become 1 over 0?
Sorry, you're breaking up. Can you repeat the question?
That's fine. So we know that 1 over 0 cannot happen in math because that just breaks a couple of rules. So what we want to do if we want to find the asymptote is to try and figure out how that we can get the function to become 1 over 0. So what x value in this function does it become y equals 1 over 0? So we want 1 over 0 to be x minus 1. Mr. Raj, what x value does this become 1 over 0?
-1.
Okay, plug in -1. We'll get 1 over, we substitute in -1, minus 1. We got 1 over -2. So you have the right idea. But what we wanted was +1. Does that make sense?
Yes, sir.
Okay, because that will come out to be our 0. So this says that the asymptote, there will be an asymptote at x equals 1. So x cannot equal 1. So how would we draw this asymptote, Mr. Raj?
Sir, could you repeat yourself?
That's fine. Mr. Raj, how would we how would we draw the asymptote x equals 1? where on the graph are all of the points where x is equal to 1? Can you still hear me?
Yes, sir.
Okay. Do you have any idea?
No, sir.
That's fine. So we know that there will be an asymptote wherever x is equal to 1. So let's say here's 1, and this is the x-axis. So we know right here is the point 1, 0. So we know that this is a part where that asymptote is. Now, if we look around, at this point is 1, -1. So x is equal to 1 at this point too. Does that make sense?
Yes, sir.
Okay. And x is also 1 here in +1, +1. Correct?
Yes, sir.
Okay. So what we can see is that all the points where x is equal to 1 are in the coordinate where x has to be 1. But that's the only condition. We do not have a condition for the y. So as long as x is equal to 1, this point is true. So that means this y value could be 1, 2, or any real number. So whatever number the y is a point on the asymptote. So any point on this vertical line is a part of the asymptote. Does that make sense?
Yes, sir.
Okay, good. So this is the line x is equal to 1. Because x equal to 1 is all of these coordinates 1 and anything. So that is this. So we can draw on our graph our function like this. So that is how we found our vertical asymptote. Now we need to know how to find our y asymptote or our horizontal asymptote. Well, we just have to look at the problem, the function, and we have to figure out what can y not be. Well, we have to see this function and see what can this function not be, because y is the function. So 1 over x minus 1 cannot be something. So what we can do is that whatever this something is, in this case, we'll just say it's y. What we can do is that we can multiply this on both sides, and we can say that 1 is equal to our function x minus 1 of a number. So this number y has to be something that you cannot multiply x minus 1 to get 1. And in this case, we know that y has to be 0. So y cannot be 0. There are 3 rules that determine horizontal asymptotes, but I will not go into them right now because we learned enough today already. But this is the general idea. of what's happening. So we know in this case that y cannot be 0. And we already said last time that y not being able to be 0 is this line here, essentially just the x-intercept. So now we got our asymptotes, and we have our function here. So what we know about the function already is that we know what the shape of the function is. The shape of the function will look something like this, that it'll wrap around the asymptotes. So since we know what the shape will look like, it will look roughly like this. And something that we can tell is that because before x can be 0 now, there will be a y-intercept as we've drawn it right here. So the problem has changed fundamentally, or the function has changed. Do you have any more questions, Mr. Raj?
No, sir.
Okay, good. So we went over a lot today, and the internet seems to not be doing the best. So what we can do is that we can end off right here and continue on with this next week. Does that sound good?
Yes, sir.
Okay. So have a safe weekend. And
You too, sir.
yeah. And I would encourage you to look at last week's lesson a little bit, because a lot of what we went over goes hand in hand with that lesson. And that lesson, I also last lesson, I also encouraged all of you to try and use Khan Academy, which is a good learning resource to supplement with not only what you're learning here, but what you'll also learn in school.
Okay, sir.
Okay. So